Hello everyone, this is Ride with a video on Recitation 5 for C222 Water Resources Engineering at Lehigh University. Today we are taking a look at a problem for pumps in combination. So essentially there are two combinations, pumps in parallel and pumps in series. And for a given pipeline system and a pump combination, we would like to find what the operation point is for such a combination. So let's start with the given. Write it down a little lower. A pump pipeline system delivers water from reservoir A to reservoir B with head at A. So let's pick the point in the surface. Of 45.5 meters. And head B of 92.9 meter. The pipe has a length of 1860 meters. Diameter of 0.5 meters. And a Darcy-Weisbach friction factor of 0.02. The minor losses include an inlet, an exit, and a swing type check-in valve. So 0.5 for the inlet plus 1 for exit plus 2.5 for the check-in valve, and that equals 4.0. The pump characteristics is given for a given Q value. What is the energy that a given pump provides is provided to you. So sometimes this is given in the form of a graph, but when a table is given, you'll still plot it on a graph, and we'll be using the graphical solution when dealing with problems like this. So we need to find, so let me just scribble here. The flow rate in the pipeline if two pumps are used in parallel combination. So Q parallel and find Q when the pumps are in series. So these are the two things we need to find out. So let's start with the energy equation from point A to point B. So HA is 45.5 meters. HB is, actually let me write it on this side, 92.9 meters. So starting with energy equation from A to B, we have PA over gamma plus ZA plus VA squared over 2Z plus the pump head. So we're using capital H, so let's just keep it consistent there. It's P equals PB over gamma plus ZB plus VB squared over 2Z plus head loss going from A to B. And this is going to be the sum of minor and major losses. So given our selection of points, we can simplify this a little bit. So that's going to be atmospheric, the PA. So is PB. Both are large reservoirs, so we can use large reservoir assumptions to take that to 0. So now we can relate the difference in elevation and the head loss to the pump head. So from here we can rearrange to get pump head equals the elevation difference plus the head loss. So actually you can just remember from this point on without having to do this derivation, but if you need to derive it, you can always use the energy equation to get to this point. So this one here is the static head, and the head loss equals, so write it this way. So then HS plus HL is referred to as the system head. We can then expand the head loss term in terms of Q using Darcy-Weisbach equation for the friction loss portion and using the minor loss coefficients for the minor loss. You can express it in terms of Q and get this final expression. (47.4). This comes from the static head plus the head loss term, 103.65 Q squared. Using this term, we can add, actually, so that static head, it is going to be the same value for all the Q's. You can add another column for system head for a Q of 0. This term here goes to 0, so you'll have 47.4 for Q of 0. And similarly, you can add the other terms for other Q values. So I have added a column for the system head. When you have pumps in series, for any given Q value, the pump heads can be added. So let's add a column for pumps in series. So I have added the column for the pump in series. Now we can plot it in the graph. So we'll start with the pump characteristic curves, and then we'll then look at pumps in series and pumps in parallel. So I have completed plotting the pump characteristic curves here. So this one is for pump 1, and this one is for pump 2. So for given values of Q's, I plotted this to get the pump characteristic curves for the two pumps. Now, if and this one here is the system head curve from this column. So the operation point is going to be the solution between the resistance from the pipeline and the energy that the pump can provide. So in this case, so let's first take a look at pumps in series. The Q's, the head values for any given Q can be added. You can do that graphically there as well. But here you have, you can get a column. So you can first calculate that and then plot it to get your pump in series curve. The operation point for pumps in series, which is now represented by this line here, and the pipeline, which is this curve, is going to be this point, the point of intersection. And this comes out close to 0.73. So this one here is the operation point for pumps in series. And this one has a value of 0.73 meter cubed per second. So this is going to be the solution for pumps in series. For pumps in parallel, so you can imagine with two pumps, the discharge is divided. So for any head value, the Q values will be a sum of the contributions for the two pumps. So if you take a look at these two pumps here, up until head value of 80, the only contribution you get is from the first pump. So HP1, up until you get to 80. At that point, you'll start getting contribution from the second pump as well. So for any other value down here, what you'll do is you'll add this portion from the first pump head curve and get a point. And you can do that similarly for other points. And So this value here is going to be added on top of this one here. So it's going to go a little off the chart here. So then, starting with the point here, actually it's a little off, you'll get a line something like this. And this now represents the pump head for pumps in parallel. So just for ease, let's say that's A over here, and you added the same length A over here, call that B. You added the same length B. This gives a easy graphical way to get curves for pumps in parallel. You could have done the same here using ruler, measuring the length, the head for pumps in series, add this one on top of this, and you can do that for a whole bunch of Q values to get your head for pumps in series. So the solution for pumps in series is then going to be given by the intersection point here, and this one is the operating point for pumps in parallel. And this one should come close to 0.56 meter cubed per second. And that here is your solution for pumps in parallel. So leading up to this problem, you'd taken a look at how pipes in parallel and pipes in series act, which was the equivalent pipes that you looked at earlier. And with pumps in parallel and pumps in series, and combining it with pipelines in parallel and pipelines in series, you'll be able to graphically solve a lot more complicated problems. And I'll see you on the next video.